So far, we've been focusing on the topic of ordered choice. So I want to take some set of possibilities and rearrange them in order, possibly not choosing all of them. Often, we also care about unordered choice. So what if I don't care about the order? I just want to know how many ways are there to pick a subset from a set of possibilities. So let's introduce this idea formally. I want to know how many ways are there to pick an unordered set of size k from a set of n distinct possibilities. Now, this number is important. It has a special name. It's often written two tall parentheses with n on top and k underneath. This is not a fraction. There's no line in the middle here. It's just two tall parentheses, n on top, k underneath. This number, or this formula here, we often call it n choose k. It's also called a binomial coefficient. And one more piece of vocabulary, the idea of choosing an unordered set, that's often called a combination of elements. So I want to know how many combinations of size k there are from n possibilities. Okay, so that's a lot of notation and terminology here to introduce at once. N choose k, written this way, is the number of ways to pick an unordered set of k, size k, from a set of n distinct possibilities. So the idea, how do we count this? Our idea, in order to figure out what the formula for this should be, is going to work as follows. Let's work from some things we already know. So it feels like this should be related in some way to the number of ordered arrangements of size k. And guess what? That is something we know. That's the number of k permutations on n elements. Okay, so I want to relate this to two things, the two components using the idea of sequential choice and the product principle. So on the one hand, let's imagine, hey, first we're going to pick an unordered set of size k. Number of unordered sets of size k. And there are n choose k ways to do that. We don't know what n choose k is yet, but we do know that it's the number of unordered sets of size k by definition. And then once we've picked an unordered set of size k, we can turn it into an ordered arrangement of size k just by picking an order. So then we're going to make this sequential choice where we're going to say, hey, first I'm going to pick the set, and then sequentially I'm going to order it in some way. So my next product here is the number of ways to order a set of size k. And guess what? We know that too. That's just k factorial. So this means we can actually solve for n choose k in terms of two things we already know: the number of permutations of size k on n elements, and k factorial. So here's our result for counting the number of unordered sets from a set of size n. So theorem, for all n greater than 0, and we have to specify here as well, 0 is less than or equal to k, and k is less than or equal to n. It holds that n choose k is equal to, and here I'm just going to isolate n choose k here, so I'm going to divide by k factorial on both sides, is equal to p of n and k divided by k factorial, which, if we use our formula for p of n and k, what this is going to become is n factorial divided by k factorial and n minus k factorial. So this is our formula for the number of combinations of size k from a set of n elements. also called a formula for the binomial coefficient n choose k. Let's do a little example calculation. So we have a group of 10 people, and we want to pick a party planning committee of size 3 to plan the best parties. Here's an example of a party planning committee. So how many ways are there to pick a party planning committee of size 3 from a group of 10 people? At this point, because we've already derived it, we can just plug in our formula here. So we know that we have a total of 10 possibilities. We want to choose 3 of them for our committee. Order doesn't matter. And so we're going to use our binomial coefficient formula. We have 10 factorial over 3 factorial, that's the number we want to pick, and then 10 minus 3 factorial, that's who's left. And then if we write all this out, we're going to get 10 times 9 times 8. Up top, I'm not going to write the rest of that because that's actually going to be canceled out by the 10 minus 3 factorial here. And then on the bottom, I'm going to have 3 times 2 times 1. And the result is 120. There are 120 possible compositions of the party planning committee. So using binomial coefficients, we can solve problems related to unordered choice. We can figure out how many ways there are to choose a group of size k from a set of n possibilities.